Hello there. In this video, I will talk about multitask self-training for learning general representation. This paper is published in arXiv in 25 August 2021 by Google Research and Brain Team. Before going to the paper, I should first apologize for not uploading video for a month. I'm moving to BC and hopefully after a month, I would upload the video on schedule again. So let's back to the paper. This paper is talking about how we can have a general model on different tasks. They said, despite the fast progress in training specialized models for various tasks, learning a single general model that works well for many tasks is still challenging for computer vision. They train a special teacher independently on labeled dataset, then use a specialized teacher to label an unlabeled dataset to create a multitask pseudo-labeled dataset. Finally, the dataset, which now contains pseudo-labels from teachable model trained on different dataset, is then used to train a student model with multitask learning. Figure 1 can show how this process is working. So we have some dataset that are not labeled, or maybe some part of it is labeled, and we want to create a model on those data sets that can work for different tasks, for example, for image segmentation, classification, object detection, the depth estimation, or stuff like that. For all of them, we want to have only one model. So what they do is we have a teacher pre-trained on different data sets. And for example, and specialize on one task. For example, we have one teacher model for classifying images pre-trained on another data set like ImageNet. And we apply it on our data set, which are not labeled or partially labeled, and we create pseudo labels. And based on some confidence level, like IOU threshold or maybe confidence of the classification, we approve those labels. And we create pseudo label dataset. Then we train a student model on these dataset. So if we come down, they said the results suggest self-learning is a promising direction to aggregate labeled and unlabeled training data for learning general feature representation. They will talk about what is the difference between self-learning and self-supervised learning. Let's go down. They are showing here one of the examples that we have of pseudo labels for object detection, for segmentation, and for depth estimation. And they mention here, Raphael and et al. Found that multitask learning generally underperformed comparing to pre-training followed by fine-tuning. So they started with some papers that basically some people showed that multitask learning is hard to train. And after some years, some other researchers trained model across multiple datasets by simply zeroing losses, for example, that don't have labels for particular tasks. So we have some semi-supervised learning that for some of the labels that we don't have, we can put loss 0, we can just mask them, and we can train, especially in NLP, we can train them. And they're showing here that there are some attempts to do this multitask self-supervised learning, and some of them are promising and successful. And then they mentioned what is self-training. Self-training is a popular technique to incorporate unlabeled data into supervised learning. The method works by using a supervised model to generate pseudo-labels on unlabeled data. Then a student model is trained on pseudo-labeled data. So this is basically what they are doing and why they are call it self-training. It's different than self-supervised learning because in self-supervised learning, we do not generate pseudo-labels. But in self-training, we first generate pseudo-label by some pre-trained models, and we train a new student model, a new model for training on those pseudo-labels. This is an example of architecture they use in their paper. So as you can see that they said the orange one, this one, it can be like the head of feature for classification. So we have some CNN layers for extracting some features, and we have classification head here. Cyan one is, which is this one, is showing the multi-scale feature for box detection and instant segmentation. So from each layer, which is very similar to FPN, the feature pyramid network, so they can do the box detection and instant segmentation. So this would be the output, the outer head of the segmentation. And the green one, it set the pixel-wise tasks like semantic segmentation, depth, and surface normal estimation. So they fuse the uh, different layers of the pyramid network. They use it for the semantic segmentation. They mentioned self-supervised training is popular method for representation learning without supervised data. By forcing the representation of an image to agree with each other under data augmentation, SimCLR and MoCo train representation useful for downstream classification tasks. They also mention recent work has demonstrated the limitation of current self-supervised learning. They found the aggressive cropping commonly used in self-supervised learning, such as those in MoCo, PIRL, and SimCLR, leads to representation that are occlusion invariant, which can be effective in downstream classification tasks. However, these representations are not necessarily invariant to other symmetric or natural images, such as viewpoint invariance, which might be necessary for other downstream tasks, such as semantic segmentation. So as you can see that most of the methods for self-supervised learning, like the video I have created about bootstrap around latent and those kind of methods, are usually doing some aggressive data augmentation, especially as mentioned here, like cropping. And these kind of cropping sometimes are not good for some tasks like semantic segmentation because they are not giving viewpoint invariant to the model. So that's why they are mentioning these, because they wanna say that self-learning is better for now than self-supervised learning. One of the other important things they mention is, as I said, when we want to create a pseudo label, we have to have some threshold on the confidence of the labels that we predict. And for detection, they use a hard score threshold of 0.5 to generate pseudo-label boxes. For segmentation, they use hard score threshold of 0.5 to generate semantic segmentation masks. If prediction confidence level or threshold was below that, they set that label to ignore. For classification, they said that they use soft labels. They just pass the probability distribution, the logits, and they said we find the performance is better than hard labels. And for depth estimation, they use simply predict the depth as pseudo labels without any further processing. There are some points here, as I mentioned in the block diagram, that they use the feature pyramid network. The ResNet is the backbone, and also they use the mask CNN for the backbone. So they mention if a student model learn from multiple tasks in the same task category, for example, the semantic segmentation and depth prediction, each task on its task-specific head without sharing their parameters. So as I said, they have different heads, so the performance on one will not affect on the others. But the last definition is here that for each task, you can have a weight, and weight can be defined based on this formulation, which coming from paper 16, scaling rule. When we have ignore label for that specific task, we can set loss to 0 to not engage that incorrect or unconfident pseudo labels in the training process. One of the important things they mention is the supervised and pseudo labels are treated equally. So even though, as I said, we have a pre-trained model and we use it for creating pseudo labels on some data sets, maybe some part of the data set is labeled by a human, and we want to combine those labels with some pseudo labels. And there are some methods that put weight on supervised labels, but here they mention that we do not batch the example of supervised and pseudo labels independently and assign them different weight, like in papers 67 and 58. The images are uniformly sampled from the union of dataset and put into the mini batches. So this will make the MUSD significantly simpler to use and scale with multiple tasks. So they just use those pseudo labels after passing those thresholds. So finally, they are showing some of the results. They're showing that when they train these models on multitask learning, when we compare it with some method like SimCLR, for some of the data set, we have better results with high margins. And only for example, for CFAR 100 for classification, we are getting a little worse accuracy. Of course, this is specifically trained for classification, but be careful that this is not trained only for classification. This is a multitask learning. Another thing they also showed here about the depth and segmentation detection. So there are some methods for supervised. You can see these kind of methods that use pseudo-label can outperform supervised learning. And there are other tables also here showing that the proposed method can outperform supervised learning by using just pseudo-label. One of the future direction they mention here is promising direction is combine self-supervised and self-learning for representation learning, which is interesting. They mentioned one of the disadvantages of using self-supervised learning against self-learning is that most of the methods are scalable with unlabeled training data. However, multitask self-supervised training can easily combine together all labeled and unlabeled data. However, self-supervised learning relies on the generalization from pre-text task to downstream tasks, which does not always give good performance. It is easier to design pseudo labels if the downstream tasks of interest are known in advance. So usually in self-supervised learning, we just try to extract some features and discriminate those features, or using contrastive learning somehow to fit those features aligned with the downstream task. But if you have pseudo labels, it can be trained using the supervised learning. So the downstream task and as the paper mentioned here, the downstream task of interest are known in this case. So MUSD generalized to unseen tasks like surface normal prediction given the task of the teacher model in this paper. So in unsupervised learning, if you want to use it for a different task or unseen task, we again have to do some sort of feature engineering, or maybe change the feature extraction or the way that we do the contrastive learning or representation learning. We have to do some modification and tweaking on that. But these multitask self-training working good on the unseen tasks. Yeah, that's it. I hope you enjoyed the video. Have a wonderful day.